This lecture will go through several what are called the gas laws that deal with changing conditions. There are many, many gas laws. This will be looking at a few isolated ones that are associated with, again, changing conditions, and I'll explain what that means. Here are some of our key concepts for this lecture. There are four basic gas measurements: pressure, volume, temperature, and moles, and those can be manipulated or changed. And when those are changed, they usually have an effect. So what I mean is, if one measurement is changed, like say pressure, if pressure is changed, it's usually going to have some sort of effect on the other measurements. Now, you can hold certain measurements constant by affecting the, say, experiment conditions, but one has an effect on another. And then there's a gas law that is associated with that, and you'll see three examples today. And so what that will become is that you need to be able to explain the relationship and then perform calculations for these gas laws. So we're going to look at, in this lecture, there's going to be three, though those five below are some that you'll be responsible for. Pressure and volume is one arrangement that we'll have, one pairing, volume and temperature, and then pressure and temperature. Those are the three that are going to be highlighted in this lecture, although there's also a pretty famous relationship between volume and moles, and then also the entire combined gas law put together. So first to gas measurements. If you think about what makes a gas particle different than solids and liquids, you may remember from kinetic molecular theory, is density. Particles in a gas are so much further apart that that has an effect on the things that you can do with them. So, for example, solids cannot be compressed very much, neither can liquids. But because gas particles are so spread out, you can really change their volume. So here are the four measurements: pressure, volume, temperature, and moles. So pressure being the force that those gas particles are hitting the inside of the container. Volume is the amount of space that they take up. Temperature is the speed of the molecules, or the average kinetic energy. And then the moles is how many. Okay, so how many particles are in there. Moles, remember, is a measurement of how many or how much. And these changes, again, if you change one, it changes the other. So if you manually increase the pressure, it's going to have an effect on the other measurements. Now, when we look at individual gas laws, some of the measurements are held constant. And again, I'll explain what that means. So we start with the combined gas law. What you have are going to be these initial and final conditions. One of the tougher parts of this is that you have to read the problems, really their math problems, carefully for what are the initial and final conditions. So you'll want to look for signal words like original or final or new or old or anything that implies initial, final conditions. Now in the equation, those initial conditions are abbreviated with a subscript 1, and the final conditions have a subscript 2. So here's the mathematical relationship between all four gas measurements. You have the pressure times the volume divided by the temperature times the moles. N is moles there. And that the initial conditions are equal to the final conditions, because all of those together are going to equal a constant. So P1 times V1 divided by T1 times N1 equals P2 times V2 divided by T2 times N2. Now, like I've said, sometimes these can be held constant, certain ones, depending on the conditions. Like if the experiment is done at standard, say, temperature, or just, say, room temperature, the temperature is the temperature, and that gas is not, it's going to have the same temperature as the room temperature. So that would be a constant. Whenever a variable is constant, it can be eliminated. So this could actually, since if it, say, was 25 degrees, 25 degrees on this side, 25 degrees on this side, you can just cancel them out. If you have the same value on each side, it can be canceled. So then you'd be left with P times V over N equals P times V over N. So any of these measurements that are held constant of course, like I said, can be canceled out. And that simplifies the equation. Those are the gas laws that we're going to be looking at. The first one will be pressure and volume. If you take pressure times volume, assuming everything else is constant, that actually equals some constant number. Starting with the combined gas law here, if temperature and moles are constant, you can, in a way, eliminate them from that denominator, and so you're left with this law. So this is our first gas law. It's the relationship between pressure and volume. It's a mathematical relationship. It's known as Boyle's law. When you do conversions, or when you do calculations, you want to make sure that these have consistent units. You want to make sure that, say, if you have pressure, both sets of pressures are in units of atmospheres, or both volumes, they're both in liters. You wouldn't want to have one in liters and one in millimeters. And now we're going to look at an animation that shows this relationship and how a change in say, a change in pressure will cause a subsequent change in volume. So here is another animation put out by the Chiral Publishing Company that I find to be very, very helpful and want to give them credit for it. The copyright goes to Mark Bishop. This is going to be showing the relationship between volume and pressure. So what you have is a fixed amount, so the moles would be constant, and then also what we are going to allow is heat to flow in and out of the chamber. So temperature is going to be constant also. So again, pressure and volume will be adjusted. Now, what you're going to see is this piston come down a little bit. So then the volume is going to decrease, and then we'll see what happens to the pressure. So there goes the volume getting smaller, and there's a little pressure gauge over here, and that went sort of up. And what you can see if you're looking in the animation, there's just more collisions per unit of time, or there's just more collisions on the walls at any one time. And again, that's a measurement of pressure. So I'm going to go back to the original, watch it come down, and watch how there just seem to be more collisions, both because they're closer together. The particles are going to collide with each other more, they're going to collide with the wall more. So that's the relationship here. A decreased volume is going to increase the pressure, and then the opposite is also true. An increase in volume is going to decrease the pressure. And so back to our pressure-volume relationship here. We have the conceptual understanding, which you just saw, but then we also do have what you'd call a formula or a mathematical relationship. So we're going to need to do some problems with that. So here are a couple of sample problems and kind of what they look like. We'll start with the basics. So just here are some measurements. This is what at their most basic, this is what they're all going to be like. The only complexity is going to be words and changing up units on you. So here's your setup. You got initial pressure, you got an initial volume. Here, 7.40. Here's your second volume, and they're asking you, what's the new pressure going to be? What's the second pressure? You'll want to do a quick check, liters and liters, so that's good. And so let's get to it. There's our formula, and we can plug them in. P1 is 1.26 atm times V1, 7.40, and that's going to equal the second pressure times V2. Doing the algebra to solve for P2, there you go. And one of the things that I love in chemistry is how beautiful the units are. So you got liters on top and liters on the bottom cancel, and that leaves you a unit of pressure, 3.18 atmospheres. And so you can also think about this from a conceptual standpoint. The volume goes from 7.4 to 2.93. So the volume gets smaller. You would expect then the pressure to increase, which it does. So smaller volume, higher pressure, it goes from 1.26 atm to 3.18. Okay, so again, that's the mathematical version of the conceptual piece that you saw earlier. Here's a second sample problem to practice, word problems. Maybe a little bit more difficult because you have to read for the context. What are the initial conditions? What are the final conditions? So a balloon is filled with 250 milliliters of air. and it's at 1.0 atmospheres. What is the volume of the balloon? If the pressure is decreased to 0.50 atmospheres. So if we decrease pressure, what's going to happen? And so at first, I think you could think about this conceptually. Smaller pressure should correlate to a larger volume. Here's our setup. I like this holding tank method on the side, where these are our variables. We read the problem to fill them in. The first pressure you're given is 1.0 atmospheres. The first volume is 250 milliliters. The second pressure, the new pressure, is 0.50 atmospheres. And the V2 is what we're looking for. Again, check your units. You're given atmospheres and atmospheres, that's good. Milliliters, and so you're going to find volume in units of milliliters. Setting it up, there's your dry formula. Plug in your numbers. Solving for V2, you get this. 1.0 times 250 divided by atmospheres. Check your units. Atmospheres divided by atmospheres will cancel, so you're left with milliliters. If ever you look at your units and they don't match up, they don't get you to the unit that you want, you know you've done something wrong. And so there's your answer. Another practice opportunity. Here it is. I recommend you maybe give this one a shot without hearing me talk through it first to see if you're getting the hang of it. So pause the video and then check your answers as we go. So going through these one at a time, your initial pressure you're given is 760 torr, because that's the original, and it's at a volume of 25 liters. If the pressure is increased to 1.5 atmospheres, that's your second pressure. What will the new volume be? Check your units. Torr, atmospheres, that's an issue. So you have to convert. Which one you convert to, it actually doesn't matter. You can just pick one. I tend to convert to atmospheres just because I think it's an easier unit to work with. The numbers tend to be a little easier. So I'm going to convert torr to atmospheres. That's the conversion. 1 atmosphere is equal to 760 torr. That's convenient. So the first pressure is actually just 1 atmosphere. Setting up your calculation. There's your unit or your formula. Plug in your numbers. Again, now we have the new P1 or the converted P1. You got atmospheres and atmospheres. Doing the algebra. And then finally your answer. So that's actually going to be the end of gas laws part 1. We've covered the intro to gas laws themselves, and then also this first law called Boyle's law, which is pressure and volume. The second part of this lecture is going to pick up with the volume-temperature relationship and the pressure-temperature relationship.